This video is about thermal resistance. It corresponds to the first part of section 32.6 in the book. What is the problem of thermal resistance? Well, basically the problem is that just about any time we have current running through devices, they're going to dissipate some of that energy as heat. That heat then warms up the device, and just about all the electronic devices we use have a maximum temperature which they can operate. So one of the things we need to do when designing any circuit which has a chance of overheating is calculating carefully how much power we can dissipate in the devices before they get too hot. Let's take a look a little bit at how we do this. Okay, so we have got a device. This may be a chip, this may be a resistor, LED, any device in which we're going to have less than perfect energy transmission. So what we've got is we've got power. How fast are we putting energy into the device? And as we put energy into the device, as it dissipates energy, that energy gets turned to heat and warms the chip up. So if we plot temperature as a function of time, if we're putting a constant power in here, what's going to happen is this is going to go up and eventually reach an asymptote. So there's two different things that we might be interested in. This looks a lot like our exponential charging curve, and in fact follows the same sort of differential equation. We may be interested in what's the maximum temperature, the temperature we could eventually reach here. We may also be interested in how fast we get up to that. Most of the time, we're interested in sort of worst case analysis, which is how hot could the thing get? And so when does it stop rising? Why does it stop rising? Well, as this thing heats up, we have power coming out of here in the form of radiation, convection, conduction, all the mechanisms for heat transfer that you've seen in physics classes. And when the power coming out of this thing is matching the power coming in, then the temperature doesn't rise anymore. We haven't got any net change in energy in the device. It stays constant temperature. So what determines how fast this power in the form of heat leaves the device? Well, that depends on just the temperature of the device minus the temperature of wherever the heat is going to, the ambient temperature. So how big a temperature difference is it? If everything was at the same temperature, there'd be no reason for the heat to leave. So we've got a cooler surround here, which is our ambient temperature, and a lot depends on, well, are we looking at conduction? Are we looking at convection? Are we looking at radiation? What are the mechanisms we use for doing it? But no matter what that mechanism is, it pretty much is the amount of power that is dissipated, the amount of heat that's dissipated is proportional to the difference in temperatures. So what we do is we divide that by a thermal resistance. So the thermal resistance here is done now in something like degrees C per watt, or if you're being a little more formal, Kelvin per watt. Those are the same unit because 1 degree C is, or a step of 1 degree C, the change of 1 degree C is a change of 1 degree Kelvin, or 1 Kelvin. So this would tell us how much power, how much heat is being dissipated from the device. So the heat coming from the device is the difference in temperature divided by the thermal resistance between the device and whatever the ambient sink is for that heat. And that pretty much is independent of what mechanism is doing it. We summarize all the different mechanisms here into one thermal resistance. One nice thing about thermal resistance is that if you've got something where you transfer the heat, say, from a chip to a heat sink, and from the heat sink then to the air. You can look at it as a chain of resistors and just add what's the thermal resistance from the chip to the heat sink, what's the thermal resistance from the heat sink to the air, add those together to get the total thermal resistance from the chip to the air. And that's basically what we do when we're trying to figure out how hot a chip is going to get. We look at how much power are we putting into the chip, or how much power is it dissipating, and what is the thermal resistance out to the ambient temperature. That'll tell us how much hotter the chip is than the ambient. Add that to the ambient temperature and you have total heat. What we're usually interested in is something that's called the junction temperature, which is sort of the temperature of the working part of the device. So if we're looking at a field effect transistor, it's where the channel is in the device. Basically, the silicon is a pretty good heat conductor, so anywhere on the silicon is about the same temperature. And so that's the junction temperature, the active part of the device. How hot does it get? And we usually have a limitation on that that's given on the data sheets. A typical one might be 150 degrees C. And so we say, how much power can we dissipate in this field effect transistor, say? We've got a transistor we're going to be switching some power with. We're worried about how hot does it get. Well, we say, well, the junction temperature has got to stay less than that. So the junction temperature has got to stay less than 150 degrees C. And if you want to be safe, you generally stay a fair amount below the absolute maximum. Then we have, well, what's our ambient temperature? And I mean, you might be tempted to say, oh, 25 degrees C, that's the room temperature. But remember that electronics devices are often inside boxes. The boxes get warm inside because you're dumping a lot of heat into them, and they don't, unless you've got a good fan blowing that warm air out again, the ambient temperature may be a good deal warmer than that. In fact, if you take a look on a lot of computers and stuff, they'll have various temperature sensors inside them, and you'll see that, oh, this part of the computer gets up to 45 degrees C, and this part gets up to 35 degrees C, and this part's getting up to 50 degrees C. You'll see different temperatures on different parts of the computer depending on how good the airflow is, how fast your fans are running, all sorts of things. So the ambient temperature here is something you've really got to pay attention to because it's often much higher than what you're thinking of as room temperature. So let's say, as an example, that the ambient temperature here is 40 degrees C. Okay, the junction to ambient temperature there, we need to have that to be less than the difference between these. That's got to be less than 110 degrees C. So if we were going to say, well, this field effect transistor, because of the way we're using it, the amount of current we're putting through it, its on resistance, all those different things that determine how much power it dissipates, is going to be dissipating 1.5, or let's make it 1.65 watts, then the thermal resistance of whatever heat sinks and stuff we have has to be less than 110 degrees C over 1.65 watts. That's 10 over 1.5. I'm not doing this very well on that in my head. That's about 7, and that's about 7. And this is all degrees C. Oh, sorry, that's about 7 degrees C per watt. Okay, so we would have to check, do we have that much, that low a thermal resistance? And for some devices, a 70 degrees C per watt is not a particularly high thermal resistance. If you have a large transistor, that's a very easy one to get. If you've got a small transistor, tiny little surface mount one, it might be difficult to get that low a thermal resistance. So you want to check those things fairly carefully when you're figuring out how much power you can dissipate. We generally don't pay much attention to how fast things heat up. That's the thermal mass that determines that. That would be given in degrees C per joule, because it's the slope of this line. And that mainly comes in if you're doing something where you turn things on and you heat them up for just a short time. The average temperature stays low. How high does it get, sort of for those short spikes? And you will see various ways of estimating that sometimes on data sheets. If you're going to do something where you're pulsing things on for just a very short time, you can put more power into them for a short time than you could if you were doing steady state where it would warm all the way up. But for the stuff we're looking at, we generally won't worry about that one very much. The primary thing to be concerned with is just the thermal resistance. And that's mainly a function of the packaging and the heat sinks that you've got. And so it's not something that's necessarily easy to get from just a single data sheet. Often the data sheets will give you, okay, assuming that this is kept at it's on a heat sink, a very large heat sink, which is kept at very low temperature, then you'd have this much resistance from the junction to the case of your transistor. That's not good enough for the calculations. You usually need to take into account the entire chain all the way to the ambient temperature. Okay, I think that's probably enough on thermal resistance for now, so that's it for this video.